Today, I'm going to be talking about the binomial expansion theorem and going over a couple of examples utilizing the theorem. First, let's remember that a binomial is a polynomial with two terms. For example, 4x squared minus 15 is a polynomial, and more generally, we can express a binomial in the form a plus b. Let's try to multiply a plus b by itself multiple times to see if we can find a pattern for the simplified result of a plus b to the power of 0, a plus b to the power of 1, a plus b to the power of 2, and so on. First, we'll see that a plus b to the power of 0 is simply 1, because anything raised to the power of 0 is 1. Next, a plus b to the power of 1 is a plus b. If we want to find a plus b squared, we'll just take a plus b and multiply it by a plus b. And using the FOIL method and multiplying out all the terms, we get that a plus b squared is a squared plus 2ab plus b squared. Next, if we want to find a plus b cubed, we'll take the result of a plus b squared and then multiply that result by a plus b. So if you multiply out all the terms and combine like terms, we'll see that a plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. Let's just focus on the expanded version of a plus b cubed and see if we can find a pattern for the exponents in the result. Notice that the exponents for a in the result starts from 3, goes down from 3 to 2 to 1 to 0. So the exponents of a go down. And then if we look at the exponents for b, we'll see that they start at 0 and then go up from 0 to 1 to 2 to 3. So the exponents of b go up. Let's take a look at the coefficients of the various simplified results we found when multiplying out a plus b. We said that a plus b to the power of 0 is 1. Next, we said that a plus b to the power of 1 was a plus b, which I'll rewrite as 1a plus 1b. For clarity's sake, I'm going to put the coefficients for each term in black and the remaining terms in light blue. Next, we said that a plus b squared is a squared plus 2ab plus b squared, and that a plus b cubed is 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. The coefficients of each expansion make up something called Pascal's triangle. Pascal's triangle is simply a number pattern that's built in the shape of a triangle where the first row just has a 1 at the top, and then we continue placing numbers below it in a triangular pattern. So the edges of each row are 1s, and each number in between them is the numbers directly above it added together. For example, notice that in the fourth row of the triangle on the right, we have 1, 3, 3, and 1. The edge numbers are both 1, like we said, because the edge numbers of each row have to be 1, except for the first row. And for the fourth row, the middle two numbers are 3. Why is that? If we look at just the first 3 in that row, we'll see that the two numbers above it are 1 and 2. And 1 plus 2 equals 3. So that's why we get that first 3 in the fourth row. Here's some patterns to remember when working with binomial expansion. Remember that the first term's exponents start at n and go down to 0. And the second term's exponents are going to start at 0 and go up all the way to n. And in order to find the coefficients of each term, remember that the coefficients come from Pascal's triangle. And it actually turns out you can find a particular coefficient by using n choose k, which remember equals n factorial over k factorial multiplied by n minus k factorial. N corresponds to the exponent and k corresponds to the index of the term. So for example, you can rewrite Pascal's triangle using combinations and n choose k. For example, if we wanted to find the coefficient of the second term for a plus b to the power of 3, we're going to look at the fourth row of the triangle on the bottom right. Why are we looking at the fourth row and not the third row? Because remember that the first row in Pascal's triangle corresponds to an exponent of 0. So if the first row of Pascal's triangle corresponds to exponent 0, then the fourth row of the triangle corresponds to exponent 3. And if we wanted to find the coefficient of the second term for a plus b to the power of 3, we're going to set n equal to 3 and k equal to 1 because the index starts at 0 and goes to 1. So the coefficient in that case would be 3 choose 1. With these patterns in mind, let's try to find the expansion for a plus b to the power of 4. Remember that we said that the exponents of the a term go down. So in this case, a's exponents are going to go down from 4 to 0. So it's going to go from a to the power of 4 to a to the power of 3, all the way down to a to the power of 0. If we look at b's exponents, the ordering of the exponents is going to be the opposite of a's. So b's exponents are going to go up from 0 to 4. So adding the b terms to the above result, we'll get a to the power of 4 times b to the power of 0 plus a cubed times b to the power of 1, and so on until we get, in the last term, a to the power of 0 times b to the power of 4. Looking at the coefficients and using Pascal's triangle, we'll see that the coefficients are 1, 4, 6, 4, 1. And if we go ahead and add the coefficients to the above terms, we'll get this result. And if we simplify by removing the 1 coefficients and all the terms with an exponent of 0, we'll get a final simplified result for a plus b to the power of 4. There's a general formula that we can use to find the expansion of a plus b to the n. And it can be expressed as the summation from k equals 0 to n of n choose k multiplied by a to the power of n minus k multiplied by b to the power of k. Remember back to your combinations section that n choose k can be expressed as n factorial over k factorial multiplied by n minus k factorial. And n choose k is called what it is because it expresses how many ways you can choose k elements from a set of n things. For our first example, let's try to expand 2x plus 3 to the power of 4. In the binomial formula, we're going to let a equal 2x, b equal 3, and since the exponent is 4, we're going to let n equal 4. Here's a reminder of what the binomial expansion formula says, and all we have to do now is plug in a, b, and n into the formula above and simplify. So substituting into the binomial formula, we get that 2x plus 3 to the power of 4 equals 2x to the power of 4, that's going to be your first term, plus 4 multiplied by 2x to the power of 3, multiplied by 3, and so on, all the way until we get the last term, which is 3 to the power of 4. If you go ahead and simplify, you get a final answer of 16x to the power of 4 plus 96x cubed plus 216x squared plus 216x plus 81. For our second example, let's try to find the 10th term of x plus 2y to the power of 16. In order to do this, we're first going to find the value of n. And if we're going to try and find the pth term, let k in the binomial expansion formula be p minus 1. We know that n equals 16, and since we're trying to find the 10th term, p equals 10. And that means k equals 10 minus 1, which equals 9. Remember that a particular term in the binomial expansion says that a term is equal to n choose k multiplied by a to the power of n minus k multiplied by b to the power of k. And we said that n equals 16 and k equals 9. So plugging that into the formula above, we see that we get 16 choose 9 multiplied by x to the power of 16 minus 9 multiplied by 2y to the power of 9. After doing some algebra and simplifying, we find that the 10th term of x plus 2y to the power of 16 is 5,857,280 multiplied by x to the power of 7, y to the power of 9. Thanks for watching and hope you enjoyed.